When executives look at a pristine analytics dashboard, it is easy to assume that information naturally organizes itself, seamlessly coalescing into a perfectly structured format. But the source of those metrics is a relentless, petabyte-scale barrage of raw JSON logs, intermittent IoT signals, and unstructured transactional data. This diagram illustrates why traditional single-server architecture fractures under this load. As data volume, velocity, and variety increase, the central processor bottlenecks. The physical limits of the hardware are reached, and the system fails. Handling these scales requires a transition to distributed data pipelines, architectures designed to decouple storage from compute to bypass those physical hardware constraints. To examine the mechanics of these systems, we have partnered with Royal Research to deconstruct a functioning, enterprise-grade retail analytics pipeline. We will trace the data flow backward, moving from the final executive dashboard down to the raw sources that feed the cluster. By reverse engineering this pipeline, we can observe how the Hadoop ecosystem acts as an enterprise backbone, providing fault tolerance and scalability for modern analytics. Behind the final Royal Research dashboard sits the processing layer, where mathematical transformations convert raw events into business-ready metrics. This layer must manage two conflicting requirements: executing massive daily batch operations while simultaneously running sub-second anomaly detection. This is Yarn, yet another resource negotiator. It acts as the cluster's traffic controller, dynamically allocating CPU and memory across a grid of servers. Within this grid, MapReduce executes heavy, straightforward batch workloads. It is a framework that prioritizes absolute resilience over raw processing speed. Running in parallel is Apache Spark. By utilizing in-memory execution, Spark handles complex, multi-step ETL transformations much faster than disk-based alternatives. Finally, Spark Streaming or Apache Storm are allocated dedicated resources to compute continuous real-time event data for operational dashboards. These varied processing engines do not compete for resources. Yarn manages the physical infrastructure so they can run concurrently without interference. Decoupling the compute engines from the hardware via Yarn prevents resource starvation, ensuring that massive batch jobs don't interrupt real-time business intelligence. Below the compute layer lies the bronze zone, the foundational layer where immutable raw data is physically stored. This is the Hadoop Distributed File System, or HDFS. It splits massive files into uniform blocks and distributes them across the cluster for durability. To ensure data stays available, HDFS replicates every block. If a physical node fails, the system immediately retrieves a duplicate from a healthy node, preventing data loss. HDFS also enables data locality. Instead of moving terabytes of data to a central processor, the system sends the compute tasks to the specific nodes where the data blocks already reside. This strategy minimizes network transfer overhead, which is a major performance bottleneck in large-scale processing. While HDFS is excellent for durability, raw data blocks are difficult for analysts to query using standard SQL. Apache Hive solves this by providing a SQL-like interface. It structures raw HDFS data into partitioned analytical tables that are easily accessible for reporting. Alongside it, Apache HBase provides fast NoSQL key-value lookups, allowing the pipeline to map session IDs and customer segments in real time. Layering these query tools over a replicated file system provides an environment where data is resilient against hardware failure, yet instantly accessible for complex analysis. At the very edge of the architecture are the countless external source systems that generate the raw data. Ingestion is a critical point of failure. If data enters the system malformed or duplicated, every downstream calculation is compromised. We use 3 specialized tracks for intake. Apache Kafka ingests continuous, real-time streams of user events and IoT signals. Apache Flume is configured specifically to aggregate high-volume application logs and telemetry data directly into HDFS. And Apache Sqoop handles the periodic bulk transfer of structured data from relational databases. All 3 pathways must adhere to a core engineering principle, idempotency. Idempotency ensures that the system can safely replay a data stream after a failure without ever creating duplicate records in the storage layer. Using specialized ingestion tracks and strict idempotency acts as a safeguard, ensuring that volatile external data is safely translated into the governed Hadoop environment. With the components in place, we can see the full scope of the pipeline, from ingestion and storage to processing and the final dashboard. In a system this complex, a single failed job can cause a cascade of errors across the entire architecture. Orchestration tools like Apache Uzi or Airflow manage the pipeline using a directed acyclic graph, or DAG, defining the strict sequence of dependencies. This layer coordinates schedules, handles automatic retries for failed tasks, and manages notifications across the entire workflow. Reliability also requires human governance, such as clear data contracts that align producers and consumers on exactly what the data should look like. Teams must also implement early validation checks and optimize file partitions to ensure the system remains performant as it scales from terabytes to petabytes. The Hadoop ecosystem provides a governed, fault-tolerant path that transforms raw data into actionable enterprise insight.